Okay, good afternoon everybody, and welcome to this Dalton Expert Insights Seminar Series. This is an event that's been put on for the 20th anniversary of the Dalton Nuclear Institute, so this is a series of expert talks which features some of the kind of most expert, insightful people we can reach across the nuclear industry for this series. I'd like to welcome those of you in person to the Henry Royce Institute Hub Building, Centre for Advanced Materials Research. Just a bit of housekeeping before we start. There is a fire drill at 2 p.m. on Tuesdays, which will be the klaxon for the end of this event, unfortunately. If there is an alarm between now and then, it is real, and you will have to exit the building from the front and join the fire assembly point in front of the Greenhouse Cafe. So, without further ado, today's speaker has over 30 years' experience researching nuclear fuels and reactor designs, which covers all major reactor designs. From various roles he's held both in the UK and the US with British Nuclear Fuels Limited, UK National Nuclear Labs and Westinghouse US. Advisory roles he has held in the past or currently holds include the UK's representative on the International Atomic Energy Association's Technical Working Group on gas-cooled reactors and the Very High Temperature Reactor System Steering Committee. He has been the chair of the Very High Temperature Reactor Fuel Cycle Board and member of both the UK Government's Nuclear Innovation and Research Advisory Board and the UK Nuclear Regulators Independent Advisory Board. Here at University of Manchester, he has since 2008 been the Westinghouse Chair of Nuclear Fuel Technology and Director of the Rolls-Royce Nuclear Technology Centre. Please welcome Professor Tim Abram.
Thank you very much indeed, Matt, and thank you for everybody for coming this lunchtime. I hope it wasn't just the cakes, although the cakes are definitely worth pointing out for those of you who haven't discovered them. I shouldn't have said that, should I? That will prompt an exodus. So thank you absolutely again, Matt, for the very kind introduction, and for colleagues in the Dalton Nuclear Institute. Thank you very much for the invitation. I'm not sure I can promise you either expertise or insightfulness, but I'll do my best. Those of you, and it's a distressingly large number, I'm afraid, who I can see in the audience that have sat through my lectures in the past, I'm sorry. Well, first of all, I'm just generally sorry, basically, but you will recognise quite a few of the slides, nuclear recycling and all that. So if it isn't absolutely brand new, you'll be able to point it out. It's also a little worrying that people with a great deal more expertise in some of the things I'm going to be talking about today are indeed sitting in the audience looking at me rather sternly right now. So I will deflect all questions to my learned colleagues at the end of all of this. So, right, let's crack on, because the other thing that people who have sat through my lectures before are well aware of is that I just can't keep to time. So I'll do my best. Nuclear fuel, it says at the heart of nuclear power, and it is actually. I know I'm a bit of a fuel obsessive. I've worked with it all of my life, actually, all of my working life. But it really is. If we think about nuclear energy, the nuclear energy itself, all the power comes from the fuel. Without the fuel, there is no nuclear energy. Fuel is right at the heart of nuclear power. A reactor is just a device for harnessing the energy and doing something useful with it. All the actual power, all the energy comes from the fuel. But not only that, all the danger sits in the fuel as well. Not quite all of it. Reactors tend to be high-pressure systems, and all high-pressure systems are inherently dangerous. But fundamentally, take the fuel out of a reactor, and most of the danger has gone. So it's the source of all the danger associated with nuclear energy, as well as the source of the energy itself. So it'd be difficult to imagine much more anything that's more at the heart of nuclear power than the fuel itself. So time's limited today. I couldn't possibly begin to tell you all of the sort of vaguely interesting bits about fuel, so I'll confine myself to talking a little bit about the background. What would we like fuel to actually do? And indeed, what would we like it not to do? And there are quite a few things that we would like the fuel not to do. What does it look like? Turns out it looks like a whole range of different things, and I've got a few items to show you, a bit of a show and tell, just to give you some indications of what bits of fuel might actually look like. In terms of bits of fuel, well, what materials do we use? I mean, uranium, of course, clearly that has to be in there somewhere. But what other materials ought we to make fuel out of? And are there any materials that we should seek to avoid, stuff we shouldn't make fuel out of? How does it differ for different reactor designs? That in itself could occupy a good couple of hours of our time. So I'll try to condense that down quite a bit. I'm going to talk a lot about what happens to fuel in a reactor. Unless we know what something is supposed to do, then it's very difficult to think about how we should design it and what we should make it out of. So quite a bit of what I'm going to talk about this lunchtime concerns what happens to this stuff when we stick it inside a nuclear reactor, and what can go wrong. There's a whole plethora of different things that could go wrong. Can we anticipate some of them? Maybe we can take measures to avoid it, or at least mitigate what might happen when things go wrong. And then, last but definitely not least, I'll be talking, basically bathing in the reflected light of the fabulous work that my colleagues are doing here at Manchester. We'll be talking, or I'll be talking about some of the really, really great work, and it wouldn't be wrong to call it world-leading work that some of my colleagues are doing here at Manchester. Just by way of a disclaimer, because we have a whole breadth of different expertise here at Manchester within the Dalton Nuclear Institute, so I should make it clear that I'll be talking predominantly about solid fuel. There are many other types that my colleagues will be more than happy to discuss with you at length, but I'll be talking about solid fuel for thermal spectrum reactors, so I won't be saying too much about fast reactors. I might mention them, but only in passing. Most of what I'll be talking about is for thermal systems. And fission reactors. The fuel cycle for fusion reactors is a whole new and interesting thing all of itself. I won't be talking about that as well today. So that's what I'll be covering. So let's crack on. It's really interesting to remind ourselves of how much energy we get from nuclear processes compared with chemical processes, compared with normal combustion burning. We talk about burning fuel. In fact, we use units that are these rather strange units of energy here that we call burn-up. But it's not a combustion process, it's just an analogy. It's to make us feel comfortable with something that we extract heat energy from. We call it burning, it's clearly not burning. But how does it differ from burning? At least energetically, very, very different. If we look at some of the comparisons, eating chocolate, for example, if we compare it using these rather strange units that some of you will have come across before, but many might not have done, megawatt days per tonne. Surely if we are talking about units of energy, then surely we should be talking in joules, or at least joules per unit mass, joules per gram, or kilojoules per kilogram. No, we talk about megawatts, we're multiplying it by time, days, and then dividing by weight. Why on earth do we do that? I have genuinely no idea, actually. The only analogy that I can offer you is that it's very similar to the way that we buy our electricity. We don't buy electricity in joules or kilojoules or megajoules. We ought to, but we don't. We buy it in kilowatts, so a unit of power multiplied by time, kilowatt hours. So power multiplied by time is indeed energy, but why don't we just buy it in units of energy? Absolutely no idea, apart from the fact that having spent a lifetime in engineering, I am still not sure I would recognise a joule if I fell over one. I'm not sure what a joule actually does for you. I'm pretty sure I know what a kilowatt does for you. My kettle uses about 3 kilowatts. If my kettle's on for 20 minutes, that would be a very full kettle. But if it was, it would use a kilowatt hour of energy, and that's sort of tangible. I feel that I understand what a kilowatt hour of energy actually is. If I converted that to joules, no idea, genuinely no idea. So, putting aside the slightly craziness of the units, let's just do a comparison. If we eat chocolate, that apparently releases about 0.2 megawatt days per tonne. Considerably more enjoyable than burning gas or irradiating nuclear fuel, but actually energetically not that interesting. If we burn gas, we get about double that. Current generation of pressurized water-cooled reactor fuels, or light water reactor fuels, give us about 50,000 megawatt days per tonne. So many orders of magnitude more energy than we release from chemical processes. If we could follow Mr. Einstein's advice and totally annihilate the fuel, then we know that perhaps by the most famous equation ever written, E equals mc squared, if we could totally annihilate the fuel, we would get far more energy again. We don't get that much, but 50,000 compared with less than 1 is a very useful amount of energy. So it just drives home that the amount of energy that we release from nuclear processes that go on within the nucleus of an atom are far, far more energetic than anything we can achieve by burning fossil fuels. And that's a hopeful thing for the future. Okay, so fuel designs. What do we want our fuel to do? Or indeed, what do we not want it to do? Well, first and foremost, we want it to provide a reliable barrier to the release of reactivity. I mentioned that nuclear fuel is the source of all or most of the danger with regard to nuclear power. Generally speaking, if we think about a nuclear reactor, there are 3 barriers to protect us on the outside from whatever's happening on the inside. They are, in order, the nuclear fuel itself. That's the first barrier. If we could produce nuclear fuel that we would guarantee would never fail, then all of our problems would be over. We wouldn't need a high-integrity reactor system. We wouldn't need a high-integrity containment building. All of that would be redundant. If we could design fuel that never failed, all of our problems would be over. We can't, unfortunately, or at least we can't do it with economic effectiveness. It's rather like saying, well, as engineers, we could certainly design a car that you could drive off a cliff and walk away from. Absolutely we could. It would be absolutely unaffordable, huge balloons that would absorb all the energy, lots of impact barriers. The whole thing would be completely crazy, but we could do it. Nobody could afford to drive it, but we could do such a thing. Similarly, we can manufacture nuclear fuel that would never fail. It would be hopelessly uneconomic. So we have to get that balance between what is affordable and what is desirable in terms of safety. So the first thing that the fuel has to do is provide a reasonably reliable barrier to fission product release. Not perfect, but reasonably reliable. What else do we want it to do? We actually want to get heat out of the thing. So we need to design our fuel in such a way that we facilitate heat transport. We want to be able to persuade the thermal energy generated from fission to find its way out of the fuel where we can do something useful with it. Turns out that in most nuclear power, at least nuclear power that we've used to date, that doing something useful with it is really, really narrow. We boil water. That's pretty much all we do. We boil water, make steam, expand the steam through a turbine, and do something with the rotating energy that we get out of the turbine. Usually we drive a generator. If you live your life on a submarine, no, most of that power goes to the propeller shaft at the back. Not all. We also generate electricity, but most of it goes to the propeller. But essentially that's all we've ever used nuclear power for, by and large. We boil water, produce steam, mostly expand the steam through a turbine. If we're serious about decarbonisation, and I suggest that probably most of us in the room today are, then we really have to expand those horizons. In most developed countries, our energy usage is roughly 1/3, 1/3, 1/3. 1/3 electricity, 1/3 transport, 1/3 heating of various types, either domestic heating or industrial process heating. If we are serious about decarbonising, then we have to address all of those sectors. And at the moment, nuclear only addresses electricity. So that's a challenge for future reactors and therefore a challenge for future fuels. How can we develop fuels that will facilitate the use of nuclear energy across all these rather different sectors compared with how we've traditionally used it? So facilitating heat transport, really important. What else do we want it to do? Well, one thing we don't want it to do is, or one thing we don't want the coolant to do, is erode or corrode the fissile material. So we want the fuel to provide a good barrier to that happening. We would like it not to relocate into a more reactive configuration. That in itself is probably the subject of a separate lecture on its own, so I'm not going to say any more there. If you're interested in what I mean by that, please come and see me afterwards, or even better, come and see my colleagues who will give you a much better explanation than I could. But we don't want it to suddenly become more reactive. And ideally, we want the fuel to provide something that we call a compact structural unit. Many of you will know that the fundamental unit of nuclear fuel is a fuel pellet. If you've never seen a fuel pellet, it's about the same size as the top joint of your little finger. Just under 10 millimeters in diameter, 12, 14 millimeters long. It's really small. If we had to put those things individually into nuclear reactors and then take them out again at the end, that would be a real pain. So we don't want to do that. Somehow we want to amalgamate the fuel together into some kind of compact unit that we can lift in and out of the reactor to facilitate refueling. And all of that we want to do at the lowest possible price. We want it to be economically competitive, and ideally we want it to facilitate whatever options we might choose for what to do with the spent fuel when we take it out of the reactor. I'm not going to say anything about that, but one of my old friends and colleagues from BNFL days, Fiona Raymond, is going to talk to us on exactly that subject this Thursday. So I really encourage you to go along and find out what those options for spent fuel management are, and how the fuel that we manufacture and put into the reactor can actually influence those options for what we do with the fuel at the end of its life. So that's what we want it to do, or ideally what we would like the fuel to do. How do we actually meet those challenges? Well, in a whole range of different ways, actually. This is as good a time as any to set the ball rolling. That's one type of nuclear fuel. Howell, can you catch it? Pass the whole thing around. Don't throw this. This is this is a bottom inlet nozzle from a PWR reactor. So have a pass of that around. Have an examine of it. This is a grid from a boiling water reactor. It's actually from a reactor called Dodivard, which was a small natural circulation boiling water reactor in the Netherlands. So some of the bits I'm going to be talking about, you'll see here. As a supplemental question for any engineers in the room, for which there is absolutely no prize whatsoever, at the end I'm going to ask you how you would actually manufacture that bottom nozzle, or how you think that bottom nozzle was manufactured. No prizes, so don't spend too long on it. Right, so what do our fuel bits look like? The smallest individual component that satisfies all of those functional requirements that we talked about, we call a fuel element, and they come in a whole variety of different shapes and sizes. The one I think that we are most familiar with is the one illustrated on the right-hand side, which is a fuel rod. We've all heard of fuel rods, even if we've never actually seen one before. Generally, they're very, very long, tall, whippy things. They have very little structural strength on their own, so we bundle them together, usually in a square array. But the fuel rod is sort of the classical thing that we think about for nuclear reactors. But even fuel rods come in a variety of different shapes and sizes. Our old gas-cooled Magnox reactors, which shut down a long time ago in this country, utilised a whole range of different fuel designs. And the graphitic sphere that is being passed around and somewhere, that's an example of a completely different fuel element. It's called a fuel pebble for something called a high temperature reactor. So it's possible to design our fuel in a whole range of different physical configurations, but by far and away the most common is this thing called a fuel rod. The rods themselves are not, or very rarely, loaded directly into a reactor on their own. They're grouped together in some way to form that compact structural arrangement that we identified as something that we wanted in our functional requirements. So when we group them together, we produce something called a fuel assembly, and it's that we move into and out of the reactor as one big structural unit. The bottom nozzle, the big heavy stuff that's working its way around the room now, that's the stuff right down at the bottom of a PWR fuel assembly. It's quite small, but the assembly itself is rather tall, somewhere between 3.5 and 4 meters tall, depending on exactly what design of reactor we're talking about. Sometimes in the British gas-cooled reactors, we arrange the fuel rods in a slightly different way. These are 36 rods arranged as 3 concentric circles within a graphite sleeve. So this is where we get most of our nuclear energy from today in this country, but only in this country. We're the only people in the world who operate this rather peculiar design, although very effective design of nuclear reactor. So that's what we mean when we talk about a fuel assembly. How might these fuels have changed over the years? Well, some of you will be aware that we have developed this so-called generational approach to naming nuclear reactors. We talk quite often in terms of advanced reactors being generation 4 reactors, and the very first ones that we built typically are generation 1. So generation 1, an example of that would be the very first Magnox reactors that were built in the UK, the very first CANDU reactors that were built in Canada. Generation 2, in fact, are most of the operating reactors in the world today. Reactors that were built during the 60s and the 70s and perhaps the early 1980s. Most of the world's water-cooled reactors, so pressurized water-cooled reactors, boiling water-cooled reactors, most of those we would describe as generation 2 systems. Generation 3 is a little bit nebulous. Somehow, at some point in time, generation 2 transitioned across to what we might call 2 or 3. They're broadly the same reactor technologies. They just use slightly updated, normally safety systems. So whereas generation 2 systems might use entirely analog electrical control systems, generation 3, we start to see the onset of the use of digital instrumentation and digital control systems. But the real change comes with generation 4, where we're actually introducing a whole different range of technologies. No longer are we confining ourselves to cooling our reactors mainly with water. Now we're interested in, for example, obtaining higher temperatures from our reactors by cooling them with gas, for example, or by obtaining even larger amounts of energy from very, very compact cores, where we call fast reactors. And here we might need a coolant that is far more effective even than water, certainly much more effective than gas. For those reactors, we tend to use liquid metals, sodium predominantly, although we have occasionally used other things like liquid lead, for example, or a eutectic mixture of lead and bismuth. So generation 4 reactors call for a very different type of fuel, irrespective of what they are, whether they're gas-cooled reactors or liquid metal, so sodium-cooled fast reactors. So not just the fuel itself, but the type of reactor it's going into has a really strong effect on what the type of fuel might look like that we have to design. But that's the physical appearance of the fuel. What are we actually going to make it out of? What materials might we use? So here I'm talking predominantly about the fissile material. There's an equal presentation that could be given on the cladding material, and then again on the structural material that we use, for example, to manufacture the grids that are being passed around and that bottom nozzle that are being passed around. But in the interest of time, I'm going to confine myself just to talking about the fuel materials. And again, it's a really good idea to start with the basics. What do we want this stuff to do? Before we actually decide what materials are available to us, let's define what it is we want the fuel material to do. So flowing on from those functional requirements, we would like the fuel generally to withstand whatever peak operating temperatures they might encounter in the reactor, and ideally including accident conditions. So not just normal operation, but if something goes wrong, what are the maximum temperatures that the fuel could be exposed to, and ideally would survive? So not melting is an obvious one, but things don't need to melt to degrade. They can degrade in very many different ways without actually getting to the melting point. So ideally our fuel material, not only would it never melt, it wouldn't actually degrade in any way, irrespective of what temperatures we subject it to. It won't deteriorate with burn-up, with the production of energy, and it won't deteriorate with irradiation damage or the build-up of fission products. We'll talk a little bit more about that in a moment. It would lock on to, it would retain all of the volatile fission products. So the fission products are the things that are produced when uranium-235 undergoes fission. If you're wondering what they are, the answer is every element in the periodic table, as we will see a little later on. All things are fission products, some more than others, but everything is, in the end, a fission product. The volatile ones are the ones that can move, the ones that can become mobile, that can become gaseous and actually escape from the fuel. And we're really keen that those volatile fission products would retain or would keep themselves locked within the fuel structure. If they never leave the fuel, then by definition they can't be harmful to anything outside the reactor. So the perfect fuel would lock on to and retain these volatile fission products. It would never release anything. And ideally we would like our fuel material not to absorb neutrons. Neutrons are the lifeblood of the reactor. They are the thing responsible for sustaining the chain reaction. Turns out we pay a lot of money for neutrons one way or another. We don't want the fuel material itself to excessively capture neutrons. So, fine, great. We don't want much then, do we? What could we use? What could we possibly use? Well, a whole range of different materials, obviously, but as an initial subdivision, we might think about metals and non-metals, for example. Most fuel that we use today would fall into the latter category. It's some kind of ceramic material, and as we'll see in a moment, most of it in fact is uranium dioxide. But that wasn't always the case. We started off in the nuclear industry using predominantly metallic fuel. So why did we change, and why shouldn't we use metals today? There's a table that some of the audience members will have learned in order to pass their examinations in nuclear engineering. I don't encourage you to learn it, but this is an example of how we might think about the two broad categories of materials, so metals and ceramics, and how they might perform against some, not arbitrary, but some attributes that might give us an indication of the favourability or otherwise of the choice between ceramics and metals. I don't pretend that the list is exhaustive even, but it's fairly reflective of the sort of thing that we would want from these materials. So in no particular order, let's think about ease of manufacture. Human beings have been making things out of metal for a long time. We're quite good at it. But we've been making things out of ceramics for quite a long time as well, and we're not bad at that either. Generally, metals, it's a bit easier to make things out of. There are more processes that we could employ to make things out of metals. We can fabricate them, we can cast them. Ceramics, a little bit more complicated. Generally, the processes are not quite as straightforward, but both fine. We can do both. So perhaps a small victory for metals in terms of the first attribute, but it's definitely not a slam dunk. It doesn't mean that we can't consider ceramics as well. The next two sort of go together. So thermal conductivity, the ability to conduct heat, and melting point. It's fairly obvious why melting point would be important. Maybe it's reasonably obvious why thermal conductivity would be important too. We want heat to be able to get out of the fuel, be transported to the coolant, where it can be taken away and we can do something useful with it. But actually, these two things go together. The thermal conductivity of the fuel material influences the temperature at which it normally operates. So if we've got fuel producing a given amount of power, if the thermal conductivity is very high, the normal operating temperature of that fuel will be quite low, and vice versa. If the thermal conductivity is really low, normally the fuel will be operating at quite high temperatures. The melting point is fairly obvious. That's where things go wrong, go badly wrong. So you can think about the combined effects of these two as being safety margin. This is the temperature that we normally operate at, and that's governed by thermal conductivity, amongst other things, but predominantly by that. This is the temperature at which things go wrong. This is the melting point. And what's really important is the difference between the two. That's our safety margin. That's the thing that we want to maximize. It doesn't really matter whether both numbers are low or both numbers are high. Doesn't really matter. Might matter for some other reasons, but in terms of safety margin, certainly safety to melting, then it's the difference between those two numbers that really matters. How, therefore, do they compare? Well, metals, very conductive, of course they are. Very, very conductive compared with ceramics. Ceramics, really variable. Some of them are quite good. Uranium nitride, for example, at 20 degrees C, has a thermal conductivity of around about 17 watts per metre per K. The units are fairly irrelevant here. What matters is the difference between them. Uranium dioxide down at 9, so compare that against the metal itself, which is almost 28. Uranium dioxide, it won't surprise you to learn, therefore, on the basis of this, is actually, from a material science point of view, considered to be an insulator. So we make our fuel out of an insulator. That's probably not the best idea until we look at melting point. Metals, well, pure uranium metal melts at just above 1100 degrees C. Uranium dioxide, 2,860 something, depending on which source you look at. So an incredibly high melting point for UO2. So even though UO2 is a really bad conductor of heat, and therefore, under normal operating conditions, operates at quite high temperatures, the safety margin, when we look at where things go wrong, is really high. So surprisingly, somewhat, UO2 is a pretty good choice. Yeah, it's not good at conducting heat, absolutely not, but the melting point is so high that we can accommodate that. We can get away with that because the safety margin is very big. Density, why on earth should we be concerned with fuel density? Why should that matter? Simply because density is an indication of how much material you've got in a certain volume. If your reactor volume is fixed, and it is, you're not going to suddenly make your reactor much bigger overnight, then the density of the material you can put in it tells you how much fissile material you're putting into the core of a reactor. If you can double the density, you've put twice as much fissile material into the same reactor as you could otherwise, which means that either you can get more power out of the reactor or you can operate it for longer before you have to shut down and do a refueling. So actually density really matters, surprisingly. Metals, very dense, extremely dense. If my head was made out of uranium, and there are those of you who know me might think that perhaps a similar kind of density might be obtained, then yeah, my head would weigh about a ton if it was made out of uranium. It's very, very dense indeed. Ceramics, lower. Again, quite variable, but much, much lower density than metals. Typically half if we're thinking about UO2. So UO2 is still pretty dense. If you compare it with a cubic centimetre of water, the density of about 1 gram per cc, then this is 10 times or almost 11 times higher, but still nothing like the same density as uranium metal. So big win for uranium metal when it comes to density. Chemical compatibility, so in other words, might it start reacting with the substances that it comes into contact with? With a metal, yeah, generally, they are prone to oxidation. I'm definitely no chemist, but one bit of chemistry I do know is that pretty much everything wants to be an oxide, sooner or later. And metals are no different. They are particularly fond of becoming oxides. And even when they are oxides, it's reasonably easy to persuade them to become higher oxides. So UO2 isn't the end of the story. UO2 can be oxidized to U3O8 or UO3. Generally, though, that happens less in ceramics. Once something is already an oxide, it's more difficult to persuade it to become a higher oxide. So generally speaking, ceramics are much more compatible chemically with things, metals more prone to react. And finally, radiation stability. So we're going to put these materials into the core of a reactor. What's going to happen to them? What's going to happen to their structures? Well, quite a lot, actually. Everything is affected by radiation. Absolutely everything. Nothing is immune, perfectly immune to irradiation, with the possible exception of some of the noble gases. So helium, for example, is almost unaffected by radiation, but pretty much everything else, and certainly everything with a solid structure, is very badly affected by radiation. Metals particularly so. They swell, they distort, they crack. We can add alloying additions and they help, but they don't eliminate the problem of radiation damage. Ceramics also, but to a smaller extent. Ceramics are less damaged by radiation than metals. There's a whole bunch of reasons for that, but generally, if we just take that as a statement as read, ceramics are somewhat more stable under irradiation than metals are. So if we take all of that together, it's a bit of a victory for ceramics generally. It doesn't mean we can't use metals, but overall, the balance of advantage lies with ceramics, of which there are a great many options. So I'll be talking, if time permits at least, I'll be talking a little bit later about some of these different options and some of the work that my colleagues are doing to look at them. Carbides, nitrides, silicides. There are different composites, so we don't need to use single materials. We could use mixtures of materials. There could be mixtures of ceramics, mixtures of metals, whole different range of different things. Things called inert matrix materials that we don't have time to go into here, but that's a kind of a special purpose vehicle, if you like. An inert matrix fuel is one that doesn't breed new fissile material. That's particularly interesting if your mission in life is to destroy fissile material. Sounds a bit odd, but there was a period about 20 years ago, particularly in the European Union, when it was felt that the best thing to do with plutonium was destroy it in a reactor. If you're going to put plutonium into a reactor, the way that we do that today is to incorporate it into fuel that contains around about 10% plutonium, and the rest of it is depleted uranium, simply because it's cheap and we know how it behaves in a reactor. Problem is, if you put depleted uranium into the core of a reactor, it absorbs neutrons and turns into more plutonium. So the stuff you're trying to get rid of, on the one hand, is also being created in the same fuel at the other time. The way to get round that is to replace the uranium-238 matrix with a so-called inert matrix, something that isn't going to absorb neutrons and transmute into more plutonium. Yttrium-stabilized zirconia was a particularly favourite material for that. So lots and lots of options for advanced fuels, and yet every reactor in the world, every civil reactor in the world, is fueled with uranium dioxide. So why? Why is UO2 so dominant? Whole range of different reasons. I'm not going to go into all of them, but we already talked about the high melting point. It's very compatible with all the materials it might come into contact with. We know how to make it. If you're going to combine uranium with another element, then one of the things we said we wanted was elements that don't gobble up neutrons. If you were going to produce a league table of elements that absorb neutrons all the way down to elements that are pretty much transparent to neutrons, oxygen would be at the bottom. Nothing else is quite as transparent to neutrons as oxygen is. So it's a really good choice from a reactor physics perspective. In terms of what we're going to do with the fuel when we take it out of the reactor, basically there are only two fundamental options. We either store it for a very, 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 very long time, or we recycle it. As far as we know, UO2 is compatible with both of those things. We certainly know how to recycle it. Storing it for a long time, the oldest nuclear fuel we have is about 70 years old. That's the age of nuclear power. We don't have anything older than that. So we've got some of this old fuel. Periodically we look at it, looks all right, hasn't degraded that much. So the best we can say is that so far so good. 70 years, is that an indicative kind of time? No, it isn't. If we wanted the fuel to, or the reactivity of our spent fuel to decay back down to the same levels as the uranium ore that we dug out of the ground, we would have to wait 300,000 years or thereabouts. 300,000 years. Quick quiz, what is the oldest thing, the oldest man-made structure, or the structure that people have made that you can think of?
Some of the cigarettes in Samaria predate the pyramids.
And they would be how old, do you think?
5,000, 6,000 years old.
Excellent. Great. So I have learnt something today, even if the rest of you haven't. So it turns out that in Samaria, there are examples of structures that are even older than the one I usually point at, which is the Great Pyramids, which of course were not built at a single point in time. They were built over a period, and the oldest of them are about 5,000-ish years old. Turns out that we've got a new winner, 6,000 years old. 6, not 300,000 years, 6,000 years. That's a big ask. It's one of the biggest asks in nuclear power. How do we persuade people, how do we persuade the public, and indeed ourselves, that we can successfully isolate materials from the environment for a period of time over which people have never ever built structures? And it's not a small extrapolation. It's a really, really big one. So that's a big thing. As far as we know, UO2 is stable over long time periods, but we don't really know. And finally, the real killer, at least as far as the good people upstairs who make interesting new fuel materials on level 7 is concerned, the really rather depressing story is that the nuclear industry is incredibly conservative, and getting it to consider new things is really, really difficult. Which is a shame, because we've got some really good ideas for new things, and we think we could do a lot better, and we probably can do a lot better. The problem is everybody is hooked on oxides, so it's not a question of just being a little bit better. In order to persuade the industry to move to a new type of material, we would have to demonstrate that we are significantly better. Maybe we can. Maybe we can. But in a nutshell, that is why oxide fuel is so dominant. So, fine, we're going to make all this wonderful fuel. I'm now going to zip through in double quick time what actually happens to it when we stick it in a reactor. So loads and loads of different things. It undergoes fission, fine. It's a really quick thing to say, but when we start thinking about some of the numbers, they are absolutely mind-blowing. Every single atom within the core of a nuclear reactor is affected some way within 3 minutes of us turning the reactor on. There are around about 10 fission events in every cubic micron every second in the core of a reactor. There's a lot going on. In a single pellet, there's about 6 trillion fissions per second. They produce primary damage that occurs of the order of femtoseconds, migration of defects that occurs over time periods typically of seconds, and the property changes that result from these nuclear events can take hours or days or even months to manifest themselves. But there's a range of time frames, but the events itself are affecting pretty much every single atom within the core of a reactor, and they do so in an incredibly short period of time. I mentioned before that with this thing about fission products and fission yields, when we put the fuel into a reactor, it contains uranium and oxygen. When we take it out of the reactor, it contains every single element in the periodic table, every single one, and indeed several elements that are not in the naturally occurring periodic table. Neptunium, plutonium, americium, and so on. So it's a real chemical soup when we take the fuel out of the reactor, and therein lies a major problem, because no longer are we concerned with just the interactions between the uranium and the oxygen and the fuel materials that they might come into contact with. Now we're concerned with the interactions of every element in the periodic table with our fuel cladding and our coolant and everything else that the fuel might come into contact with. So the fuel chemistry alone is mind-bogglingly complicated. It produces neutrons, of course, fine. It gets hot. Yeah, it gets really hot. If it's UO2, the center temperature of typical light water reactor fuel will be about 1,000 degrees C, give or take 100 degrees C or so. The temperature on the outside, the coolant temperature, is just over 300, about 330. So a very significant temperature gradient across a fairly small distance. A pellet is around about 4.5 millimeters in radius. The temperature difference between the outside and the inside is very large, roughly 500 degrees C between the center and the surface. So we have temperature gradients of over 100 degrees C per millimeter, and they're driving events like diffusion very, very significantly. In terms of a thermal analysis of the problem, thank goodness it's only essentially a 1D problem. Heat travels radially. It really doesn't travel circumferentially, and it really doesn't travel axial at all. So essentially it's a one-dimensional problem, but it's still a major problem, still some major thermal gradients going on in there. The fuel expands and it contracts. We don't really have time to go into why it expands like this, but it actually does. And this is not really a nuclear effect. It's an effect that you will observe in any brittle material that is exposed to a parabolic temperature gradient. In other words, higher temperatures in the middle, smaller temperatures on the outside. So it's nothing to do with the fact that it's in a reactor. This is the fact that this brittle material is trying to expand significantly in the middle and trying not to expand very much on the outside. It cracks. And it cracks in a pattern that looks vaguely like this. So we expect to see these radial cracks, and we expect to see these circumferential cracks on this sort of r theta plane as well. Does it really do that? Well, it depends on your imagination. So here are some micrographs of cracked pellets. If you stand back far enough and squint at it and sort of say, oh, well, yeah, you can kind of see some radial cracks coming out here. They're not quite like the neat pizza slices that I showed on the previous diagram, but it does happen. It does happen in broadly the same way that the theoretical models would predict. So indeed, the pellet does crack. When does it crack? Well, pretty much straight away. As soon as we go up in power, as soon as the reactor has reached full operating power, our nice, beautiful, fully dense pellets have all cracked, all of them. And that itself leads to other problems as well. It sinters. Sintering is part of the manufacturing process. It's part of a process where we manufacture all kinds of ceramic materials. We take our nice ceramic, we bake it, and it becomes that characteristic hard material. We call this sintering. Sintering is a major part of the manufacturing process, but it doesn't stop there. As soon as we put the fuel into the core of a reactor, the sintering that we started when we made the fuel in the first place just continues. And the fuel continues to get denser and denser. We deliberately don't make the fuel 100% dense to begin with. We leave about 5% of porosity in the fuel pellet, and that provides a place for some of those fission products to actually go. Provides little reservoirs where the fission gas can be accommodated inside the fuel. But the problem is, as soon as we put the fuel into the reactor, that 5% becomes 4.5, and then 4, and then 3.5, and it just continues, and eventually that densification levels out. So here we're plotting the pellet volume, that's where the pellet started, and we've got these two competing effects going on. One of them is causing shrinkage, and that's this densification process. So the pellet is just getting denser and denser and denser. But that process starts quite quickly and then levels off and becomes almost flat. Why do you think that happens? You know the answer. I'm not even talking to you. Yeah, so we started at 5%, and then we get down to 4.5, 4, 3.5, 3, 2.5. Well, eventually, the pellet's fully dense. We can't sinter anymore. We've already sintered out all of the porosity. So So densification stops at some point in time. But this other line, this one that carries on monotonically going upwards, is swelling. Every time a fission event takes place, we trade one atom for two, and sometimes three, but mostly two. And then another fission event takes place, and now we've got two more atoms. Well, one of those could potentially sit on one of the lattice sites occupied by the uranium atom that underwent fission. But where's the other one going to go? It's forced into interstitial positions, planes of atoms are forced apart, and at an engineering scale, this manifests itself as a swelling of the fuel. And that swelling is just a linear function of burn-up. Burn-up, remember, is just the amount of energy that we get from the fuel. It depends on the number of fissions. You double the fissions, you double the burn-up. But every one of those fissions is causing swelling. So the more and more energy you get from the fuel, the more and more and more it swells. And if you add those two effects together, you get something that looks like the Nike swoosh. So initially, the pellet shrinks, and then we hit a sort of a minimum pellet diameter, and from that point onwards, the swelling just continues. And that fuel pellet will continue to get bigger and bigger and bigger the more we leave it into the reactor. So we've got all these effects going on at the same time. Eventually, because the cladding is moving downwards and the pellet, as we've just seen, is heading in the opposite direction, that's getting bigger, eventually the two contact together and we get these bonding layers between the cladding, the metallic cladding, and the oxide fuel. So we get these bonding layers. What we're seeing here is a micrograph, so the fuel has been irradiated. We've taken it out of the reactor, so it's cooled. We've got shrinkage, and what we're seeing here is a cooling crack. The fuel pellet is trying to shrink back to its original dimensions. So is the cladding, but the cladding shrinks a little less, and we get this cooling crack opening up between the two. So we get a strange interaction mixture where we've got pure cladding material up here, pure UO2 plus a load of fission products down here, and a real mixture in at the interface, which is partly oxides of cladding material, partly oxides of fuel, and fission products themselves. And some of those fission products are quite troublesome because they cause things like stress corrosion cracking. So the halogens, particularly anything like iodine or cesium, will tend to go into cracks, and we get potential failures of the cladding material at stresses which are much, much lower than the characteristic yield stress that we would expect to get. So we get cracks forming across the cladding. Right, and we release fission gas. We get lots of fission gas from the fuel, and here are just some examples of fuel that's been undergone microscopy. So we can see these populations of gas bubbles at the grain boundaries of the fuel. As the fuel irradiation continues, we can see that we get something that looks like the craters of the moon. So the fission gases accumulate in these bubbles on the grain faces. You can see those long cigar-shaped gas bubbles at the grain edges. They haven't actually joined together yet, but that's where they're going. They're joining together. We call it interlinking. And eventually we get fully interlinked pores where it's a little bit like a maze, but you can imagine if you were a gas atom that found its way to a grain edge, then the grain edges are all pretty much open. The gas vents. It's released into the voidage inside the fuel rod. The pressure inside the fuel rod therefore starts to go up. And the whole network of gas passages collapses because the thing that was keeping it open was the gas pressure inside. Once that gas pressure's gone, those network of bubbles tend to sinter again, and they will close, and the whole process begins again. So fission gas release is not a nice linear process. We get little bursts of gas being released. The gas bubble network collapses, and then a new gas bubble network starts to be created again. So we get sort of these little bursts of gas actually being released from the fuel. And its microstructure evolves in really interesting ways that we don't have time to discuss, and as a result of all of that, sometimes the fuel fails, which is very sad. We won't go into all the phenomenon, but here are some pictures of fuel failure mechanisms. We talked about pellet cladding interaction and these cracks being exacerbated by the presence of a stress corrodant, normally iodine in our case. The fuel can corrode from the outside. Once it's corroded, then hydrogen that's liberated from the corrosion reaction can be taken up by the cladding, and that gives rise to secondary failures called secondary hydriding. Crudding is a whole separate discussion on itself. And every so often, we get rubbing that takes place between the grids and the fuel rods, and we get these so-called fretting scars, where simple rubbing between the fuel rod and the grid gives rise to a hole in the fuel rod. So the fuel fails in some fairly interesting ways. Generally, it's pretty reliable. Current failure rates are down at about 20 parts per million, roughly of the order of 10 to the minus 5. So it's pretty good, but it's not perfect. Anyway, this is what we're doing to make things better in the last 2 or 3 minutes that we've got available before the fire alarm sends us on our way. So our group's working on advanced fuel materials. So Lin Yi is working with Matt on TRISO fuel developments. This is a bit of equipment that's upstairs on floor 7. This is our new toy that we're very, very proud of. It's our CVD coater. This is what we use to make TRISO coated particle fuel. Manchester has been doing this, by the way, for rather a long time. Ping Xiao's group has been doing this for, what, 15 years, Ping, would you say, roughly, on non-uranic samples, so simulated kernels, either alumina or zirconia kernels. But fundamentally, the coating mechanism, the way that we coat these things, we've been working on here at Manchester for a very long time. I don't think any other university in the UK can point to a similar history. But now we've got the ability to manufacture coated particle fuels using actual uranium kernels. We've not done it yet. We're not quite confident in our abilities yet, but we're learning and we're getting there. So some really good work is being done on TRISO fuel developments. We're looking at how we might get over the problem of conductivity. I'd said that UO2 is a really bad conductor of heat, and so it is, but I also said that it's a really popular fuel. It's very difficult to wean people away from using it, which is equally true. So how do we square that circle? Well, one way might be to find ways of improving the thermal conductivity of UO2, and one example of that might be to include some something like molybdenum from in the fuel. So molybdenum, obviously a metallic element, will improve the thermal conductivity without, we hope, inadvertently affecting the good properties of UO2 that we'd like to keep. So Fihan is currently working on that. We've got a new PhD starter called Robert Orme who will be taking up that work and running with it. Other advanced fuel materials that we're looking at, so I mentioned there were a lot of alternatives to oxides, and so there are. We have in the past looked at silicides as well. We're currently doing some really good work on nitrides, so Max and Megan have been working for quite a while now to manufacture samples of uranium nitride fuel and to investigate what we think is maybe a bit of an Achilles heel of this material, which is the fact that it reacts with water and steam at a much greater rate than oxide does. So if we had a fuel failure in a water-cooled reactor, obviously we've got the possibility of water getting into the fuel rod and an energetic reaction taking place between the fuel material and the water. So we think we've got some potential solutions to that. One of them is currently being patented at the moment, but we've got a lot of work taking place on advanced fuel materials, at the moment centred around nitrides. Rob Harrison is leading some work along with Han, looking at radiation damage in some of these advanced fuel materials. This is a collaboration that we're undertaking with Oxford. We're using their atom probe to look at the nature of radiation damage. And once we understand the damage mechanisms, then we can think about looking for ways to perhaps not avoid, but at least alleviate the consequences of those damage mechanisms. Another major announcement that was made very recently is that Rob Rob is leading and won a major investment from the Nuclear Decommissioning Authority around the construction of a plutonium ceramics academic hub. So many of you will be aware that the UK, to its embarrassment, has the world's largest stockpile of separated plutonium at the moment. Not the world's largest stockpile of plutonium, but separated plutonium. It's plutonium that we've recovered from spent nuclear fuel. In fact, if you took the United States stockpile and the Russian stockpile together, ours is bigger. It's very, very embarrassing. And we've got no idea of really what to do with it. But it's okay, Rob's on the case, so within the next 5 years or so, Rob has guaranteed that he'll come up with a solution. Being slightly facetious, but actually this is the start of a major academic piece of work. It's very difficult to point your finger at anything that has been undertaken by UK universities like this in the past. Simultaneously with this, we have installed and are in the process of undergoing early phase commissioning for a capability that, as far as we know, is unique anywhere within academia within the world. So this will allow us to work with plutonium. Very small amounts of it, extremely small amounts of it, but in a facility that was eye-wateringly expensive for very, very good reasons. So those two things coming together are really, really timely. This is a capability that doesn't exist anywhere else in any other university in the world. And even outside the world of academia even, this is a very, very rare capability. So this is really something very, very special indeed. And actually, final slide, I think we have also been looking at how we might manufacture not just UO2 fuels, but waste forms, material for incorporating plutonium into that could survive for very long periods of time, using very novel technologies. So I talked about the sintering process for manufacturing nuclear fuel. At the moment, we do, industrially, we do what we call pressureless sintering. So effectively, we take our uranium dioxide powder, we press it into pellets, and then we bake it at very high temperatures, about 1,750 degrees C, for 6 or 7 hours in flowing hydrogen, in other words, in a reducing environment. That's quite expensive. By working with our industrial partners at a company called Lucidian, we think we have developed a way of producing exactly the same material in a fraction of the time and at much lower temperatures. This could be really, really interesting from the point of view of future fuel manufacture. So again, Rob's leading that work, but Howell is involved in that work, and Johnny Morgan as well has just completed his PhD in that very subject. So I think that is it. I would invite questions, but with great skill, I've run out of time. So I draw your attention to my excellent colleagues in the audience, who no doubt will answer all of the questions that you might think of. Thank you very much for coming indeed. And just to remind everybody, we've got another talk in 2 days' time. This is Professor Fiona Raymond, who works with the Dalton Nuclear Institute. She's going to tell you a lot more interesting stuff about the possibilities that we have for dealing with spent nuclear fuel, and in particular in recycling it. So thanks ever so much for coming. Sorry I went a bit over time. That really is all. Thank you.